So, hello everyone. Right now, we are back with another session where we continue with our solving problems. And basically, I was seeing that the videos are getting around 50 views, which is quite astonishing. I thought maybe 5 or 6 views would be at most that I would get. But again, the retention time is quite low because I expect, because these are not something where you just do entertainment and stuff. And yeah, the background noise might be quite high because I live literally near the roads. So from from the corner that my house ends, the road starts within like what 1 meter apart. So that's the issue. But do keep up with that. I have some noise filters, but basically they don't work that well. Whatever. And just one thing, just a channel update. Probably I would like to have streams instead of these recordings that I do. Let's see what we do later. But if we carry on with our coding, so we were able to go till problem 7. Now we are going to start with the problem number 8, which is now more related to, if we go here, it is now problem number 8 is basically, now we are going into the level, getting the level and the level order. So first we need to think about getting the level. So uh, mm, I told you, na, like I was thinking of making two functions. Basically, if you see the question, it is saying that to make a function such that it will take a root and the particular node. But I do need one more, what do you call this? Parameter, that is the level. So if I just show you the prototyping that I did here, if we go to problem number 8, I made two functions, like not made, I just note down or jot down two functions. Let's now make it fair. Let's get level. Oh, I use capitals. This is the typing, like what do you call this, naming convention that I'm following, but forgot the name of this naming convention. If someone knows it, I shall Google it out later. Or maybe we can actually Google it out because we are actually studying. So, naming conventions. Is it conventions of variables? Okay, getting too much of noise because of the background. Okay. Mm. Camel case, Pascal case, snake case, and kebab case. Okay, that's. I remember seeing the snake case and all. I forgot which one is which. Let's just go and check real quick. And where are they? Snake case. So you basically you use underscore, right? Okay, that is good. Okay, this is called kebab case. Okay, it basically like a seed kebab. You are pushing the stick inside a video, so it's something like that. Camel case. Okay. Okay, so we are using the camel case, and this is called the Pascal case. Okay, camel case and Pascal case has just this one difference: is the first letter of the variable will be in the lowercase, while the next word in that variable will be in uppercase. So that's the only distinction between the camel case and this Pascal case. With that being said, let's make the utilities. So I told you that I need not only the data, but I also need the level. Now let's create the function. Basically, first, of course, if root equal to null, basically when you don't have the tree, so it's a very simple thing that we need to do. We need to return. Basically, okay, we are returning the level. So when you don't have anything, you return -1. Okay, or maybe we could return negative that int minimum. I think -1 makes more sense. Let's go with suppose the data that we have got is the root, means the first node. So first node or the root. Okay, so if the root data is our D, that's the element that we are searching. So then basically we just return the level that we just start at the current level, which is given at 0. We are going to do recursive call for this. So we just do return level and it's done. Now we need to do something very similar we were doing. Basically, we need to check the left subtree and the right subtree. So check the left subtree, and I can call this what? Okay, naming things. Okay, what do you call this? This is going down, down the level, down level. Let's go with down level. Down level, and we do a recursive call. Basically, we go down. If we just uh, see this tree, basically we go down from here to here, then again here, here. So not this is the left. So basically, in the recursive call, it will have to go to the right. But like after I do the right part, so so first I need to know get level util, and I just changed the root with root left, and the other things will basically remain the same, but we were able to traverse one level, so we need to increment it by 1. That's there. And if that is the case, we need to stop it as well so that it can goes to the right subtree. So do a if condition, if down level, what to do. So if the down level, it is going down, it will go and go and go. Okay, it will go till it reaches the child of this, or yeah, let's say child of, okay, child of this left. Okay, 12 ka left, so that is null. Then it will just give -1, right? So until and unless it is equal to -1, it will go. Hopefully the logic is fine. Let's do a return, and we return the down level. Next, we basically do the right subtree. We can do it directly in the return call. So get level util root right B and level. Now, do we increase the level here? Of course, because we are able to go to the right. Hmm. Will it work? That's my question. So let's imagine if it goes left and then suddenly down level equal to 1, -1. So after that, it's no longer able to do it. So then you do the root to right. So suppose it's here 12. Then after it goes to 12, like basically you do root left and go from there to null. So it's equal to then basically it goes to 13. It goes to 13 and it does an increment. After that it goes 13 के बाद 1. Then all the stacked stuff basically एक एक करके निकल जा रहा है. And after that you do it again. You do it again till you match this key. So you do it till you get the level, and level has to start from 0. Yeah. So I do think it makes sense. If there are any other implementation or improvements, I would like you to help me with that. So, mm, when this part is done, now basically in the question they have asked this function. So let's create that function right now. So, oh, by the way, is it void? Oh, it's void. Okay. And I did it as void, right? Yeah, yeah, no, wait, wait, is it void? Oh no, I was looking at here. Okay, this is not void. That's why I was thinking. Okay, so it is int. So of course I need to return the level. So get level, and I need to have bt node, the root, then int d. Basically, we do a very simple return call. Wait, we just call this. This is like a wrapper, what you call like it's literally a wrapper at this point. Do the root, you pass the d, and for level you just start with the 0, and you are done. So basically, what should I call this? A wrapper? A wrapper because of the question needs. Because of the question needs, and we're done. Should I do the level or the traversal? Right? We can actually do the level or the traversal, and in the level or the traversal, we we don't really need this. That was a very bad background noise. Very sorry for this background noise, but I told you I live literally just meters, like few meters away from the room. So let's do the problem. My mother was calling me for dinner right now. So let's do the problem number 9. And uh, will I be able to complete void level order? Did I do a capital? No, I did a small, right? So then level there is capital, this is small. Okay, okay. Level order is complete what I think. So now we just pass as per the main function the root. What has happened? Something happened. What? That was a bug or something? I don't know. So first let's do the simple check, which is root null. Basically we don't have a tree. And if we don't have anything, we do a printf. Yeah. We do a printf, like basically the tree is empty, brother, fill the tree, then talk to us. Because it is void, we can just do a return. Yeah, we are done. Not done like with the function, but yeah. Okay, so remember what happens in level or the traversing is that you can have a stack which is taking notes of the what do you call this? Taking notes of the number of traversals we are required for left and right and stuff. But uh, if you have a queue, this basically uh, makes the process easier because stack is a last in first out data structure, whereas queue is it goes in a line. Basically it's a real life line. So if that's the case, you will see the logic. Just uh, let me type out the logic a bit. Queue, let's queue what? Let's create a queue structure using the create. I hope I wrote it like this. I don't. Okay, let me just check it real quick. It was utils.c, and we created the queue structure. Yeah, yeah. So it's now we have the queue, and basically there is there have been any issues with creation of queue, then you just do a return. Because it is void, you can just do a return like this. And now, with that, we need to first, just like the previous, what do you call this? The stack implementation that we did uh, for our post order non-recursive and in order non-recursive, we need to have something very similar for this, right? So let's have it NQ का ठीक लिखा तो था हाँ ठीक NQ is written like this. NQ, now we need to NQ the in the queue we need to NQ the first node, that is the root node. So we do that. Then we can just have a like what you call this, printf level or the traversal is below. So with that, now we need to go till the queue is not empty. So is empty, if it is true, no, is empty is true, then I have to make it false, because the queue needs to store the values. So let's go like that. So is क्या लिखा था वहां पे, QMP, okay, is is capital EMPTY is QMP. Like a Q here. Hopefully it is empty. That means it's hopefully it is not empty, 0, and I need to convert it to true. Yeah, fine. So let's do the current node, BT node. Let's use the same terminology we used there, current, and we do the DQ. The DQ returns the node. Yeah, it returns the, what do you call this, first in, first out. Okay, जो पहला है उसको निकाल. So if that's the case, we are done with this part. Next, now we need to basically traverse it, and traversing के लिए एक logic दे देते हैं. Basically we will use the current. If you use the current, I can just first do a printf of basically the value, and let's use the tab key. Next, we can just print the current data. First, we do the current data, so that root printing done. Basically, I'm thinking like, okay, root, like first triangle, that root. Now, we need to go to the left. So, first, if the left node exists, so if current left is not equal to null, if it exists, then I can do a simple NQ function, NQ Q, and I can just do the current left, done. If that is true, now I can go to the right. So if current right is not equal to null, then I can just have the NQ enough to again Q Q current right. With that, we are done with this logic, and Now, how it works? Basically, in the queue, suppose you have the roots. Okay. So the root goes in, then it basically just prints the root data. Then it goes to the left, and if the left exists, it goes to prints the left data. Then if it the right exists, then it prints the right data. Then again, what happens is basically you are doing a NQ, right? So how it okay, not like mm, how should I call it? How should I call it? Uh, okay, in that printing, it happens like in each and every loop. So first it prints the root. Now, suppose in the left, it takes the left. Okay, after it takes the left, it pushes it into the queue. So now at the first line, your left data is there, and at the second position of the line, your right node just after the root is there. After that, because the queue is not empty, so is empty is false, and true basically reverse it. Now it's a true. So then you dequeue it. So you print out the value which is there. So you dequeue it. So wait, am I doing it in the correct order? Yeah. So basically, oh yeah, I was just confusing with the stacks. I was thinking it was going to print out from the right. No, because the first one that was there is the left node. So now the left node gets printed, and basically after that again the current ka left. Now what is the current? Basically the left node's current means if you just go here after 34 will get printed, you will just go here. Basically this का left है 12, उसके बाद इसका है क्या बोलते हैं 40, and then it will just go again. Now it will print the right in this one 73. Now then after it gets to 73, it will go like this 60 and 79. Then it basically will print out this whole line, and yeah, so the logic is fine. So then I can just have a printf and nothing with just simple backslash n, and I of course need to free the queue. So free queue, yeah, that's there, and free the queue in here. With that, we are done. We are done with this problem number 9. Now I do need to go and get my dinner, and then again we can start this next part. Probably pausing it will work. Yeah, so I am back and the recording has started, so let's go. So we have completed till the level ordering. Next, what question do we have is the zigzag one, right? So I think I don't need this right now. So I can see that the audio is fine. I will just check testing it. So I need this zigzag. Let's do problem. What is this? 10, right? 10. Paste. Save it. Let's save the buffer. Now, let's continue our programming. Basically, we need to do the zigzag means how much? What? Okay, I haven't looked at the question that well. So that returns the level order traversal in a zigzag alternative traversal in the direction from left to right, then from right to left. Oh man. So it is not like if I just go ahead and if I just change the ordering, like in this case, if I do it like instead of left, I do the right. So that will be a right bias level ordering. So, oh, by the way, I think we can actually write a comment here. So this is the left biased level ordering, because as you can see that we are going to the left node first, then the right node, but now we need to like basically reverse the between the two, right? So Should I use a stack or a queue? See, I think we can use a stack here because it's more like I need to do first in, first out, again, first in, first out, first in, first out. I no, first in, first out. If I do it, then I think then queue would be better. No. If I have a stack, it will be last in and last out. Then I can, should I do it one stack or two stack? Well, I can actually do uh, two stacks that will take care of the two levels. Basically, if it is like 49, then it's going from like this 73, 34, then 12, 60, 79, then 50, 38, 13. So I can create two queues or two stacks. I can create two stacks. Basically, first let me just create the root, sorry, null. Basically, when you have nothing, then you can just do a printf uh, tree is empty, and you, because it is a void, you can just do a return. Now I'm thinking of having two stacks. Let's say first stack be called the level that I want. So let's say call it current uh, level, and I just do a create stack function. Create stack for this. Okay, just a second. Let me visit. Yeah. So where is my create stack function? Where is it? Yeah. So it returns the stack here and it does the allocation without here. Okay, fine. So if I just have something called like the next level, then I can track the two levels and do the zigzag in that manner. Let's see. First, of course, we need to handle that whether these two are created properly or not. So if current current level, or if there is an issue with the next level, then basically we do if it is the current level issue, if so current level returning null or zero will basically free it. So free stack current level done. Let's go next level. If I press enter, then it just doesn't like do that smartly. So and after this to I do need a return. But someone is calling or not. Okay. Yeah, so let's continue with the coding. Now whatever. Okay. So just do a return. We don't need anything because it's a void. Now that it is done, okay, by the way, everything is going on correctly. Yeah. So now the thing is that how do we do the zigzagging? Let's do a simple primitive zigzag. Okay, let's think about it. So if I have something like this from here, from the current level, if we are thinking that basically if we follow the same template that we put it into the current, and will there be any issues? Or do we need a we need to store it somewhere? Suppose I store the current level at some temporary variable, and then okay. We need something to understand that when we are moving from left to right or right to left. Suppose I use a flag, like a very primitive way of doing it will be to use a flag. Then I can control the flow. So even before printf, I can have like in the stack, I can do a simple push current level. I can push the root into the stack, like as we have already been doing for the last few programs, or not programs, basically last few functions. We also introduce left to right, some like that kind of flag, and we, so first thing, let's go from left to right, so we have it as true. Then let's go with uh, so while, of course, is stack empty? Answer is no. Then that convert it. So is stack empty, current level, and my phone is fully charged right now. Hopefully, I won't get much call, like many more calls right now. That's also yeah, it's fine. Let's create a temporary node. Let's call it temp, and we basically just give the root to it. First stage. And we just have a condition where this node is not empty. I can just level order, so I can have the first printing of this node. So it will be current, no, not current. I have popped it out already to the temp. So basically it will be temp data. Now, the thing is that suppose the left to right is now true. So suppose we are now moving from left to right. If that is the case, then I can just have the if condition with a flag left to right, if that is true, now I need to, if I'm okay, basically I am at the root, I can just go to the next left, then I can go to the right. So mm, let me just write it down first, then I'm going to think about it a little bit. Right. mm, No, I'm going from left to right, sorry. So it should be left to right. Of course, I can just have a simple checker here. If it is not null, then only I'm going to move now. I need to make it such that in this loop, so I just do a simple print. No, if I do a simple print, uh, why is it not something? Yeah. Hmm. Now I think it will be a better time to use the next level. Check the link fine. So I can just have the next level stack store this left if I'm moving from left to right, and let me just do the logic once here. So if I'm moving from left to right, so push to the next level, basically temp left. If that be the case, mm, this will work till the current stack is not empty, and basically it will go on like that. If I'm thinking it correctly, I can just but suppose the stack gets empty, because when it pops out all the values for this left to right, but then again it goes from right to left. I need to change the direction. So if the current level stack is empty now, I need to change the direction. I need to change the direction. And what if I just swap the stacks? And what if I just swap the stacks? I think that should that be the enough? Like um so if is stack empty, wait, now I don't need this reversing. This will happen when the stack is empty. So current level, so I can just flip it by changing the left to right as whatever be the case, just opposite to it. And basically write a simple stack function. So like stackable swap function. So stack, let's do a temp stack, and I store the current level stack here. Then I do the swapping, like it is basically swap by reference logic. Uh, and then the next level will basically have the temp stack. Now, if I go back here, what am I doing? So from left to right, I'm going to the left first, then I'm pushing it. Then I'm pushing it, and then I think that's done there. And then if I just do a if here, if oh then I can just push the next level. You just go to temp right. So this is left to right. Now for this, I can just have the opposite case. Oh, I think it should work. Let's go. Basically, I just do the opposite of temp right first. Then I just push the next level. But I do the right first here. Hmm. So let's go to this logic and just check it. So if firstly the root node is there, then I just take the root node to the temp. Then what happens? I print the temp, then basically the root node. Then I move from left to right. So first in the next level stack, I have the left. That means here I should have 34. Then I will have the 73. Okay. Because it is true, I won't go there, and I'm not going to go here because stack is currently not empty. So this stack is currently not empty. Now then, if I just go ahead, mm, go ahead with this, basically that is not empty. Now I then pop out the last element would be, oh, wait. No, currently I think, yeah, basically this is empty. So I do need to swap the direction here. So that logic is fine. So if I change the direction, so I now change the current level stack and the next level stack. So basically now what happens is that I have these elements 34 and 73 in my current level stack. So now I just swap it, then goes that it is not empty, and now it pops out the elements. Basically, because it is a stack, it means the 73 will be going first, and as it pops out the data, then left to right was set to the opposite. So the else part will go. Then basically from here, wait, I think I did it wrong. Wait, why is it there too? Hmm. Did I do it correctly? So I remember seeing it at somewhere. Zig, zag, level printing in 183. Like I remember this was the logic that was shown there somewhere. They have used a 2D vector for it. Let's go and just check it once more. So what happens is basically root node there 49. Let me just create a temp right now. Let me do a temp. So let's call it what are the things that we have? We have current level stack. We have the temp stack, not the temp stack, the temp node. So this is the node. And we have the next level flag. This is the stack. And we have the left to right flag. This is the flag. So now currently it is 1. Okay. So what happens is that you have the root currently. You push the root into the current level. So that will be what? That will be 49. You have the 49. Next, what we do is we pop the 49 into the temp node, the binary tree node. Next, what we do is basically we go to the, we print it out. So remember, we are using the temp to print out. So this will be our print. So just add the print statement here. Now, next, what do we have? So because it is true, we go into the first block and there we go to the temp left. So temp left means 34 and 73. So there we push it to the next level. So we push 34 and 73, right? So we push it there. Next, what we do is basically, as you can see, it is empty. We then swap the two and we change it. So first we need to change it to 0. Then we swap 34 and 73 to current level. So this goes here, 34 and 73. And because these have now been swapped, we do need to check if it is empty. It is not empty. So it is empty is 0 and converting it's true. So it just goes into the loop. Now we pop out from the current level, that is from the stack. It should be the backmost element. That means the last element, that will be 73 into the temp. Okay, so currently it has already printed out. So I think I should just write a print statement here. So it will just go to 49. And because it now goes from 73, so it just printed, like not printed, just pasted it here as 73. Next, we do print it out. So it will be 73 printing. next what we do is we are currently, the node is 73. So we have 60 and 79. So we go here as 60 and we do at 79. And no, wait. That's not true. That's not true. Because the flag is 0 here. So we have to go to the opposite, right? So it will be the 79 and 60. That's why it was confusing, because you need to do the reversing. 79 and 60. So if I just go to 79 and 60, then basically the current stack is particularly not empty, so we don't go into that block. Then we go here, and then first we just take the current item, that is 34, and put it into the temp. So that will be 34 in here, 34. And what we do, we print out the data, which is 34. Let me just go check it out once. Yeah. So after we do that, basically what happens is we go to the left of the current node, that is 34. By the way, because the left to right flag is still 0, we do need to go from right to left. So that is 40 and 12. So that will be here. It will go as 40 and 12. So that will be there. After that, because the current level stack is empty, we need to change the flag to 1. And we basically need to cut this, like basically we need to have all this data into the current level. So we will have swapping it. So 79, 79, 60, 40, 12. And this will be deleted. So now the current is there. Basically we pop out, the last element will be 12. So we print out, first we do the assignment. So basically it will be 12. Then we print out the 12. Then basically because it is 1, we 12. So from 12 we do the left and right. Because left is null, we just do the right one, that is just 13. And basically after that, what happens? The current level is not there. So yeah, so then this goes on without that. So nothing happens in the stack empty because it is not empty. So then we go and pop out the last element from here, which is 12. Wait, did I not pop it out in the last? I think I forgot to do it. So here, so it will be 40. Then 40 will be here. And what happens is you just print it out 40. So yeah, it is working. It is going 49, then 73, 34, then 12, 40. Okay, let's just see. It can switch it from there. Yeah, it can switch it because it is basically in the stack. So yeah, our code is working. So at least doing a dry run, it is working. Okay, it was hard. It was really hard. Not going to lie. Okay, the thing is that I had this logic. See, I was having discussion with one of my friends that how do you do this zigzag. He told me to use two stacks and basically have them switch between them. So that was the idea. This is exactly not my idea. Very sorry if I ever said it's not my idea. It's one of my friend's idea. He's he's an engineer, so he does all of these kind of problems on a very regular basis. And this was probably the hardest problem in my whatever the dictionary I have. So, and basically after this, you just do a print statement. What? And you just free the two stacks. So first will be the current level stack and free the other stack. That is the next level stack. Oh man, this is done. Now let's go here and okay, so in main we do need the main.c. So after the zigzag is done, we still need to solve 8 more problems. That was just problem number 10. I just have one question to my professor. How many problems? I know that these problems were given 2 weeks ago, but again, there are too many problems though. And at this point, probably AI will solve all this. But again, going through this logics by oneself is pretty and good. It feels good. Okay. So leaf count is probably easy. You just need to check if both the left and right are null. So it's a very easy one. So I do okay. Is it returning it? Yeah, it's in okay. Leaf count and then full node, then half node. Okay. So it is end get. Okay, I forgot the name that we gave. So let's just go to binary tree.h and we just go to problem number 11. So get leaf count. So you the count and we just pass the node like root node to it. And of course, like basically, if you don't have a tree, it doesn't mean doing any counting. So root equal to null because it is int. You can't do a simple return. You just do a return 0. Uh, did I use it somewhere? Return 0. Wait. RETQRNER. Yeah. Also, I have. Okay. ETR. How many places where did I like do this mistake? Uh, I really wanted a stream. If there have been a stream, people might. Okay, there are no more. Good. So uh, now, so after you do this, you basically just check if from the root left equal to null, and you just do both of them needs to be true and root right equal to null. If both of them are true, then you basically just mm, wait, when should I do the recursive call? I can just return 1 here. Wait, what's the question here? Number, right? So can just have this counting done as a summation. So if I do it something like this, that you just return 1, and here if you just have an else statement such that you just return get leaf count to a root left and do a get leaf count and do a root right. So what happens? Root doesn't have any leaf, so it will directly go to else path, and then it will go to the left path. Then it will go again left, and since it will go to 12, and it will go that okay, this this 12 boy Okay, this will not go here. So it will go, probably it can't go to any of this node. So it will go to right. So right, then these guys have, so it will just return 1. So it will return 1 here. In the stack, it will just go the recursive call. In the stack, it will have 1, then it will be heading it up when it just releases the stack elements, and then it goes to here, releases the stack elements. Yeah, it should work. It should work. Yeah. So if we have the structure for basically, what do you call this? What do you call this basically? Leaf count. Now you can just have problem 12. I can do one thing. I can basically just go to the visual node and yank this, paste it. I'm not going to do the leaf count. Basically, I need to have a get full was what? Full node count. The node count. So this remains the same. I just change because I need to have the count. I can count variable here, and then if I just have something like this, basically a full node, right? So that none of them must be null. So instead of having both of them equal to null, I will have not equal to null. And when that happens, my condition is true. So I just do increment the count equal to 1. I set it to 1. Then in the return, I basically do something like count plus. So having get, I will do the full node left and then right. Yeah. So this would work. Okay, if we want to say that how it works, let's just go and check it. Let's go with temp. So basically what we have count equal to 0, and there will be this something like return stuff. I'm just going to say that. So currently it has nothing. So just let's check 49. So the root node, it's not null. Left and right are totally filled. So basically you just increment the count by 1. So it increases by 1. Not increment, you just change it to 1. Then you just go back and do the return. So you return 1 plus something something. So 1 plus you just do the left. So from 14 you go to 34, and there you check that okay, 34 is also a full node. So then you just do the count again, because you had something like a previous count plus you are doing the count again. So basically now you have 2, and this will work. Yeah, it's a very simple algorithm, so it's fine. Now what was the next thing that we need? Probably it was half node, full node, then half node. Okay, so if I just go here, I can just do what? This is the last thing, right? So, oh, I mean insert. So this is okay. I should have my relative numbers turned on, but whatever. Sloppy. This is problem 13. So let's call this half node. Yeah, it's all half node. Now here the thing is that there will be just a minor change, which is basically if you just go here, if left is not equal to null and basically right is equal to null, this condition needs to be fine. So I will have two conditions here like this, and I will just have this for condition here with root. Now this is left equal to null, equal to null, and root uh, right not equal to null. Yeah, and that should be fine. Oh, of course, I need to change this. Okay. Now, if that is done, we need to solve the 14th problem, which is if the two trees are identical. It basically means that mm, what do you call this? Each and every node and every traversal is the same. So it is an int, right? So let's do int is identical, and we make bt node. Now we do need the two trees, so I will have it as root 1 and root 2, just like I have there. Root, root 1 and then root 2. So of course, if there exists no trees, both of them are null. So that will be a trivial case. They are identical. So let's just do if root 1 equal to null and root 2 is also equal to null, then you just return 1. That's the most simplest case. But suppose suppose then one is null and other is not, then it is a trivial case of not equality, like inequality. So if I just have root 2 equal to null or root 1 equal to null, then I can just prove a return 0. Now I need to write the actual checking statement. So basically what happens? What happens is root 1 data is equal to root 2 data. This needs to be true when you are at the root. And along with that, the whole tree structure, that means is the left path and the right path also needs to be the same. So I can just have something like should I do it like this? Root 1 left equal to root 2 left. I need to take each structure at once. So basically I can just wrap it in the same function and use it something like this. And I just have the last thing is identical, but I just pass in one, right, something equal to, wait, hmm. Because I'm not checking the data, so it should be fine here. Like not checking the data here, just passing the arguments. So if it goes till there and goes till the null, then of course it means the same. So yeah, right, and I just do simply. Uh, how do you do this in Vim? The beginning of the, I think it was dollar sign, or it was beginning probably shift I, shift O. Let me check it. So suppose I go here. Okay, currently I'm here. So let me just return line. And I think we are done with the is identical. Uh, I think we are done. So now the thing is that the mirror one will basically be the same as this one, just we need to change the last line. So this will be problem number, what it was, 14, right? 14. So after we are done with is identical, we basically just do simply yank it, paste it, and just change में C था ना? C, right? Ah, okay, okay, okay. Okay, I did something. But I still need to get used to him a lot. So is mirror. So this is mirror. So of course, if both of them are null, basically they are mirror because you can't have an enantiomer of a point object. So did I wrote this enantiomer of mirror? Okay, no, I was doing that in the print statement. So um, next, the null statement is still fine, and the data is, of course, you have to have the equality of data, but here it will be the mean change. First of all, the function will be changing. So is mirror, and we basically just instead of like, oh, by the way, I'm not doing the, so it should be something like this, and should be right, and not should doing the equality, and this should be the इसका right, मतलब उसका left. Okay, done. Now you just, I do need to do some checking here because I messed it up. So fine. Okay, his mirror is done. Next, we need to print out all the ancestors, breadth. What do we have more? Complete tree. Oh man, too many stuff to do. Can we do it tonight? Because I also need to do the project. And that project, basically, we haven't even started. Oh, by the way, am I recording all this? Oh, yeah, I was recording. I was just having this little heart attack that I was not recording during all this. So, because now, why is there no music? At this point, I need some music. Okay. Yes. Oh, the views increased. I got some comments here. I think I replied to them. Good. I saw the views increased. That is giving me some hope in life. I don't know why I just say that. Okay, Tortoise. This is one of my really favorite songs. Basically, I really love the or official singers. They have done beautiful music, and uh, they do dubbing in Hindi. Probably they are not going to give me a copyright claim if I just play their song. I need to be very careful with people who give me copyright claims, who might give me copyright claims. But yeah, let me just check if there are any probably no interference. Yeah, the microphone is actually catching it up, so might be not good for now. I need some. Okay, I think this is the best one because the microphone was not catching it. Yeah, this is better. Okay, that was just a simple digression. Let's continue. Problem 16, 17, 18. Okay, we only have 3 more to go. Let's get pumped up for it. Problem 16. Controller. Okay, so we need to print the ancestors. What does ancestors mean? Basically, wait. Let me just check it. I don't know what happens in this song that it's not being detected in my microphone, and that is good. I need some songs to be playing. So with this, write a function to print ancestors bt node. Okay, that prints all the ancestor nodes of node. For example, ancestor 40 is here. So basically this and this. Okay, there is no order, so this is a good thing. And we use the bool for it. I don't know why. Probably just so that we can just say basically the target node was found and not found, because the user pagla hai bhai, user कुछ भी दे सकता है, user can give anything. Ancestor nodes, ancestor NCSTOR. Yes. Now I need the BT node. I know the root. I need the root. I know the root. What can we? And I need the target data. So the target node. So I just use D. I'm going to just call it target data. And I kind of like it. Target Chalo. If basically if you have nothing, then there doesn't mean why I say this, because the thing is that this line needs to be there at every intersection of the code. So notice how we change it based on the return type of the function. We change it to 0, maybe void, it means nothing. Now because we are using bool, so we are returning false, so that changes. Now if we do root data and it matches with the target data, basically means we are at the तुम्हारा भाई ancestor कोई नहीं है भाई. Basically you are at the root, you are the beginning, like तुम परिवार शुरू कर रहे हो, like okay, that went not that big, whatever. So return true. So we are not even going to print anything, so that's it. But suppose it's either in the left or the right subtree, so we can just do a simple recursive call and do it. So if print ancestors and you just do root pass the left and along with the target data. If that is okay, if this is true, if this actually matching in the left and then right, so basically in the root case it will be the root itself. So उसका अगर left और right हो गया तो फिर इसका ये हो जाए. हाँ, it makes sense. So left and right, let's do it. Print ancestors, root, right, target data. If that is the case, then we can basically just do something like this. Print F. Let's just have the data printing and we change it to P and it will be the root data. And because we found it there, we can just return true. And suppose in both of them, if we don't find it, finally we can do a return false. Is the microphone picking up the noise? Music. No, they love this music. Okay, so this kind of makes sense. It's fine. Next, we need to do get the breadth. Breadth means maximum width. Means for this case, it will be 4. So. Now this is where I hate this kind of like zigzag and all this kind of questions. So let's do problem 17, and I want to say that I have had help with from one of my friends who told me to use a queue for this. So let's just get away with doing the usual checking. Let's create a queue. And if there is some issue with creating the queue, you know what to do. Now we come to the main logic. So as always, we basically just do in the queue we enqueue the root. Okay. So after we just enqueue the queue, we can actually have a variable that tracks the width, say max width, and let's just initialize it to 0. So while the queue is not empty, so while the queue is empty, returns no, then true. So queue, that's a logic. We go inside and we do let's say no, I think this is where our building the structure. So how do I, where did I do it? In utils.c. So this is why I remember, yeah, this thing. This will be very useful right now. So if I just have it a little bit more opaque, as you can see, the one that I highlighted is q to count. Means there is this one variable that I'm going to use. Okay, where is it in the main structure? Where is the q structure? I remember making the q structure somewhere. Oh, it should be in the header, right? So yeah, this is the structure. And oh, why do I have it multiple times? So this is the count, because it counts the number of items in the queue. So if that is there, we can easily do this kind of program. So we just call it as something like level, like this is a local width counter. So level width, and I just do the counting, keep the counting here. Currently it is nothing basically, because if you just go here and no, not like, okay, you're changing. Oh yeah, just go here, and if you go to, where is it, I always set the count to 0. Okay, so currently there is nothing. So nothing means like at least not the garbage value, but 0 value. Okay, so the level width is now at 0, and if we just think about it, we need to change this particular counting. So I have the max width at 0 as well. Max width will be the global width, and the level width will be with respect to this each and every locality, basically local levels. So from there, if this level width is greater than, so I do greater than or equal to, we need to find the max width, right? So I think let's do them greater than, so it will be max width. Then basically you do the swapping, max width equal to level width, and as you do that, you just swapped it and done. But we need to do the traversing, and then adding the items, and we need to update the count. We need to do all of that. So how do we do that? That's my question. Let's use a loop. Should I use another while loop? This was right. We particularly now need to dequeue basically all the nodes. This is my target basically. So basically I want to first, whatever be there in the queue, I need to let it all out into the current level, and then for the next level I just put it back in. And if that is what I'm targeting, why don't we use let's use a for loop for this. For zero, it will do this till it is less than level width. Let's have again the same logic that we were using. Let's create a current binary tree node, and let's have this dequeue. So as you know, what it's going to dequeue? The root node right now. We have to give the root node, and of course this is going to go till the current is true, mm, now if I just go to the left, and if it is not equal to null, then what do? I just enqueue it. So we are at the left, right? So into the left. So if I just replicate the logic for the right, so this logic seems fine. Of course, I need to free a queue and basically return the maximum. So now let's see how it works basically. If I just go to temp, so right now we have too many variables right now, but we can work with it. That's the thing. Let's have max. We have level width, and we of course have the loop variable I, and we do need to track of the queue. We need to like take note of the queue, and also we need to understand what is there in current. So let's see. Now the logic begins basically when you enqueue the root. So in the queue you now have the root, which is 49, which is good. Now what do? We first okay, by the way, we have it set it at 0, and level width is also 0 because you just did the queue count. Okay, next basically both of them, so there is no greater than equal to sign working, and then I is set to 0. Is I less than level width? No, currently not, and so we don't go into that. But do we do anything then? They missed something. Oh no, we actually did the dequeuing, right? No, we did it inside that, so probably it will not happen. So is this correct? Let me think. Level width queue count is not fine. Okay, this first loop will be totally nothing. So then because the queue is not empty, we again do that, and we never go into that. Mm, maybe not go. Oh, wait. Why is Pritam? Give me a second to just. Yeah, so I had to go because suddenly Pritam just asked me to. So, like, he just asked me to review this. This is his project that he has submitted, and do I have mine? Whatever. So, uh, I was confusing this one, right? So let's go get back to it. Mm, yeah, so let's get back to it now. Yeah. So this is initial setup where what happens is, okay, you would change the count here. Yes, one goes here. So the queue it is 49. Now I was mistaking this as 0, right? So level width equal to queue count, that is 1. Level width is greater than maximum width, so of course maximum width needs to be updated. And I equal to I0 is of course less than, then current DQ, you basically in the current you DQ it, so now you have the 49 node, and in the queue you basically now have an empty queue, and you go to the current left, so 34 and 73, so you NQ 34, so 34 and 73. After that, you go back and that is done. Now, because the queue is still not empty, you do the checking. Basically, as both two nodes are there, it will be 2. Now, level width is now 2. Max width needs to be updated to this. I is again equal to 0. I is less than level width. And basically, you just DQ it to the current, and as you, because it is first in first out, so 34 will be the first one to go out, so you just go 34 and this goes here, then you go to the left and right of 34, which is 12 and 40, so you just NQ it, it is 12 and 40, 12 and 40. After that, the count will be 3, and basically if you do that, then the max width will be 3. No, yeah, it is 3. Oh, wait. Check it out. Undo. Yeah. So it goes till here, 12 and 40. But what happens is that after it does that, because it is 2, so I needs to be 1, then it DQs 73, and 73 goes here, and because of that it's 60 and 79, 60 and 79, and because of that now it goes to 4, then it updates to 4, and then yeah, so that's the logic is working. So now let's go to the, where is it? Yeah, we are probably at the end, right? So get the breath. Now we need to build this whole tree by taking manual inputs. Oh no, that was the different one. Yeah, we are okay. Build a complete. So what's the complete reference? It forms a complete binary tree with the input if the user gives a tree. A tree, display a tree and turn this. Okay. What is a complete binary tree? I always forget the definition. Complete binary tree. So if we go and check, it basically means, okay, is my recording? Yeah, it is currently recording. Why is the music not here? I want to play some other music as well. Let's play something that will not get me any kind of copyright issue. That's the only thing I don't want to have. Liz Robinette. So will playing her song will get me a copyright issue. Let's just play with this because it doesn't give me that issues. Oh no. Oh, I need to search it. History, in which every level except possibly the last is completely filled, and all nodes in the last level are as far as possible is filled. So it can have between 1 and to the power h nodes where the last the level is h. So it's a full binary tree and complete binary tree. Okay. Basically, we need to fill it up from the left, right? That's what it feels to me. So, and also there are multiple checkers that we need to do. Okay, this is going to be a long one, but this is going to be the last one. So I'm quite happy that doing the last one, but again, this is not something that will end in a jiffy. So let's just have it BT. Okay, did I use the small letter BT name somewhere? BT. No. Currently, I'm finding it to be small, not small. Oh wait. Yeah, it is. It's going to give me some issues later. Definitely. It's okay then. So let me just do it. Yeah, good enough. So that error is gone. So BT node, let's just name it. Oh, I forgot the name that again. So oh, I was using double point precision pointers here. Okay, I don't know why I use it here, but it's fine. Oh wait, I need to return the tree, right? So that's why I use it. That's why I was forgetting. Why the heck did I use again pointer here? So whatever. Let's go. Build complete tree from input. Okay. So that is there. Now let's begin the simple process of asking the user for everything. So BT node, let's create a root node, have it to null, then let's create a queue, because we do need to take the data and be it in level wise and stuff. So basically we want it to be level wise, otherwise the generally users don't sometimes like in order is not that much intuitive sometimes for most of the normal users, but level ordering must be better. So level ordering input. Okay, so let's have the queue, create queue, This here. Q done. And of course, if we just have some error in making the queue, so return, what do you return? Null. In this case, we return null. Now, we do need to give some warning to the user that please enter the data as positive integers to build the binary tree. And we can just say that if you just enter 0, if you enter 0 or let's say anything negative or negative numbers, then the then the building process will stop. This makes sense. So if that's the case, I think I should do one thing. So now that that is done, I think we can just take the root values, like root value, sorry. So enter the root or root value, whatever. Scanf. This will be percentage %d. Yeah. So I do it. If you enter something ridiculous, so I can just always have R and do it like insert R equals to this. Basically, if it happens, if R is not equal to 1, then you basically go to the main menu. You just do a return null. Should I do a return null? Yeah, I can do a return. I would have rather liked it to go to the main menu, but currently in this particular program I don't have the menu access, but I can import the main. It will be a very recursive, like butterfly kind of import. Well, we can keep it like this, or if I later want to implement it, I shall implement it later. I think it will be better if I just comment it. So if that is the case, if basically we need to first check the data purity, means if the user wants to print nothing, so basically data is less than or equal to 0, then we basically just do have nodes entered, so that tree is empty. If it is empty, we can just free the queue and we can just return it. But if it is not, then we continue with root, not root 1, root, we create the node, pass the data, and if there is any failure in creating the node, you know what we do? We just basically free the queue and we just return null. Now, if everything is fine, then we can do the NQ operation. Oh, C means you have to take care of all of this. Now, what should we do? We can do it till the user. Now we after entering the root, basically he enters the other data. So we can do it. We can have a break statement inside the like what do you call this? Unlimited, infinite while loop. So there we create another node. Say this takes care of our current parent, current node. Let's call it current or current parent. Current. I use it again and again. So it's this parent, and basically we just put the root node here. DQ. Who's that? Oh, Elizabeth. Okay. If now if there were issues with making this current node, which I don't know might happen, current parent. So then we just do a break and we go. So that's there. But if there are no issues, we can just carry on. Now we can just do a printf, ask the user to enter the first. Let's go from the left. So left child left child, let's say for the node, I do something like this, %d here. I think that looks good. And we can also have a disclaimer or note, something like that. Basically, if you do something like less than or equal to 0, then you can skip this. Skip this node. Skip this. So if that's the case, then we can have, so there is one %d parent data, then we just do a scanf %d, we scan it to basically data, and then again we do need to again do the checking key user basically wants to stop or something less than equal to 0. Then if it is less than equal to 0, we can just NQ the current parent. No. Yeah, we can actually just keep the current parent because we DQ नहीं NQ किया था. Yeah, we did the DQ, so we need to again take it inside. So Q current, wait, sorry. Oh, no, there is no type. Current parent, and we just break it. So now if the user doesn't want to break out, so basically it means current parents, because it was the left child, left, which basically we need to create a node with the data, and if we create it with the data, then we do need to go to the left. So Okay. Now this is true. Now that we have made this is not like null, we can just do an enqueue the left child there, the current parent left, and that's fine. And if it fails, basically we just do a break. Okay, let's do it here. Break. That should make sense. Now, this was for the left child, but now we need to do printf. We need \n, enter the right child or the node again. I can also give out a node here, node less than or equal to 0, skips this node. So that is there. Then basically it just follows the same logic. So, oh, so the music started. It was stopped for a while. So we took it now if the data is less than or equal to 0, then basically we break out of it. If it's not, then current parent का right में जाना, वहाँ पे node create करना with the data, and if the current parent right node gets created properly, just put it into the queue. I hope they did not do a break. Yeah, yes. Break. Yeah. So we are now after that. Basically, we need to free quit. Free the queue. Printf. Let's do a final print. 3 building is complete. Good enough. Now that we have completed it, we can just return the root. Oh, make our root and we are done. We have completed the first assignment, and the thing is that we still can't run it because the main function is still left to be done, and I'm thinking what to do. I still have to make a lot of things here. Main.c. Basically, I need to create the main function, and we also need to create these extra functions that I want to do. Not this one, sorry. This one, random tree, and this hard-coded. So I need to make these. And also we need to solve the problem set 2. We have a lot of things to do at this point. So how much time? Today we spent another 2 hours trying to complete. So in all it took us about what, 1 hour plus 3 hours plus 2 hours, so it's 6 hours. 6 hours just to complete the first assignment. And we still need to complete the second assignment. Oh, let's see. Let's go. So that's it for today. See you all in the next video where I do the next assignment. That's the binary search trees. And probably in the last video, we shall be completing everything with a whole script that basically runs all them. So the main. Goodbye. See you. Good night.